I'm going to talk about MFEM-MGIS and MFront, which is an MFEM-based library for nonlinear solid thermomechanics. A little bit about the outline. So I will give you some context and goals of the project, which is very close to the previous ones, the ones of the previous goals. So it was very, very interesting to see that talk. I will show you a small tutorial about where we ended up in our design. And then I will give you some design and features of the MFEM-MGIS project. I will give you also some feedbacks on issue that we have currently with MFEM, and then examples and conclusion perspectives. So I mostly work for the French Atomic Energy Commission, which is a public institution, in the Department of Nuclear Fuel Modeling and Simulation. So we have developed in this context a numerical platform, which is called Pleiades, which helps us to model a lot of nuclear fuel elements for different kind of nuclear system, standard pressurized water reactors, sodium reactors, and that kind of thing. So we have application dedicated to all of this nuclear systems. And we have developed advanced physical models based on top of those nuclear systems. So we have using non-brew finite element solver at CEA, which is great for nonlinear computation, but it's not well parallelized for the moment. So we were looking for solutions where we could handle the nonlinearity of our problems in a parallelized way and very efficient way. About my work, I mostly work on MFront, so I'm rather computational mechanics, and all the physical information are coded in MFront, which is a code generator, which I will talk about later. The main point is that we have to deal with a wide range of materials, so ceramic, metals, composites, and a wide range of mechanical phenomena and behaviors. So we have to deal with viscoplasticity, plasticity, swelling, irradiation effect, ductile failure, phase transition, and that kind of things. So it's very, very complicated physics and metaphysics problem that we have to deal with. And we also have to deal with a wide range of mechanical loadings, because when we are dealing with normal operating condition, the typical time scale is the year, while when we are dealing with off-normal operating condition, the time scale can be the microscans to a few minutes. So the main goals of MFEM-MGIS is to build a general-purpose nonlinear multiphysics library. The development began at the end of the last year, so it's pretty recent. And our primary focus is nonlinear mechanics and heat transfer. And we expected to model in the long-term shell, beams, phase field approach to brittle fractures, micromorphic models, coastal plasticity, and all the complex phenomena that we have to introduce in our modelization. We have decided to base this on two parallel libraries with open source commitment. So the first one is MFEM, so that's why I'm talking today. And the second one is MGIS-MFront, which I'm currently the main developer, which deals with the constitutive laws and material modeling. So just to see what we are talking about, this is an example of the end user API that we came up with. So this is just to show you that it's very high level, and we tried to do something similar that what the previous speakers wanted to do, something that could be usable by standard engineer. And this is very declarative in C++. So we're using C++17, and we declare a nonlinear evolution problem. We pass the mesh file. The parallel aspects are hidden by default. And we define material names, boundary names. We define the local behaviors that we want to deal with for the given materials. So here the notch beam is described as a mechanical material, and we we take the behavior in an external library that is passed via a string. And then we set the external state variables for this material and add boundary condition at post-processing. and then we look over the time steps. So basically, this is the kind of API that we want to expose to our users. So the main entry point is the nonlinear evolution problem class. So everything is derived from this class. And with respect to MFEM, the main new concept is the concept of behavior integrator that I will describe later. So one of the bases of the project is MFront, the MFront generator, which is dedicated to all the material knowledge that we have to use. So it can be material properties such as Young modulus, thermal conduction, that kind of things. Mechanical behaviors, so we can support for small and finite strength behaviors, cohesive models, and also generalized behavior, just like non-local or multiphysics. And we also have to introduce pointwise models, which describe all the physical evolution and chemical evolution of our materials under irradiation, just as swelling. So this code generator has three main goals. First one is numerical efficiency. The second one is portability and coupling capabilities with a lot of finite element solvers. And it also meant to be easy to use by end users. And we have a lot of tutorials about this. The second library is MGIS. It's a library which provides classes for solver developers to retrieve all information about a behavior and set up the memory, which is used to store the internal state variable of the material, the equivalent plastic strain, the damage, everything. So everything is done at runtime. So you take a share library generated by MFront, and MGIS handles all the memory allocation associated with the behavior, and also provides the necessary methods to run the behavior integration at the local scale. So it's written in C++ with bindings with C, Fortran, and other language. And it is being used and tested in many solvers, Phoenix, OpenGeosis, Kratos, MFEM, and other ones. So the idea is to use this part to couple MFEM and MFront behaviors. So the added values of our project, we have made the statement that there is a post-support to multiple materials MFEM for solid mechanics, in the sense that it was not easy to define part of the mesh to be elastic and part of the mesh to be plastic. So we had to deal with that and add support for this kind of things. And there was also no support for function on integration points. So what we call partial quadrature function, for examples. So the proposed improvements was to add support for nonlinear behaviors integrators based on MFront, add function and integration points that depends on the material identifier, which is the element attributes, and the simplify high-level API that I showed you earlier. So in practice, it's a library which is made of classes which inherits from MFEM and classes which inherits from MGIS, which deals with all the aspects of materials management, internal state variables, and that kind of things. It's C++ 17, open source, and you can download it at this address. And we are dealing with tutorials at the second address. So what we have done is that inside a specific nonlinear form, we just forward the computation of the residual and the stiffness matrix to what we call behavior integrators based on the element attributes. So this allows us to have different behaviors on parts of the mesh. So some parts can be plastic, some parts can be elastic. And basically what does behavior integrators is that at each time that I need to update the residual, I compute the strain, I perform the integration, so I called the MFront behavior, and then I do the assembly of the inner forces, the residual. And I do the same with the element stiffness matrix. So behavior integrators are called in the assembly loop for those two computations of the residual and Jacobian matrix. So behavior integrators are meant to compute the gradients from the unknowns. So depending on what you are treating, whether it transfer or mechanics. So the example that I've given was for small strain nonlinear mechanics. It handles the state variable of the material, so equivalent plastic strain, damage, everything that's needed. It called the behavior integrator, compute the inner forces, and compute the stiffness matrix. And this depends on the kind of problems to be described. So mechanic, transfer, symmetry of the material, isotropic, orthotropic, and modeling hypothesis, 3D, plane strain, plane stress, axis symmetry. To be honest, writing a behavior integrator is pretty much tedious and error prone. So it has to be done with care. So what we have done is that we have written a small code generation tool to write those behavior integrators for us. So because I fear to lack time, I don't know if I still have time, but I won't describe this slide, but we have a small code generator. It's far from being equivalent to something like the OFL of Phoenix, but it's already quite handy, and we can do a lot of things with that. There were two issues that we wanted to give you. The integration of the mechanical behavior can be seen as a very complex kernel at the integration point, where we had to solve an ordinary differential equation, and this can fail. The problems is that the method of MFEM, just like nonlinear form integrator, assemble vector, or assemble element grad, does not handle such failures. We have made a workaround by building our own Newton algorithm, which separates the behavior integration step from the computation of the residual and stiffness assemblies. So that works pretty much with hyper linear solvers, for example. But it also seems compatible with partial assembly, which we haven't tested yet, but this is our goal in the near future. However, this workaround does not work with PETC integration, for example. So it's, for us, it's a bit limited as a solution. And we think that we should maybe try to improve the robustness of the operators MFEM. And we started a discussion with the main developer on GitHub with this. So this is a work that I hope to have time to work with them in the near future. The second problem that we face currently. Yes, tell me.
5 minutes left in the talk.
Okay, perfect. It's the handling of Dirichlet boundary condition. If we have a look at this beam, what's happening? We have the configuration at the beginning of time step, and when the nonlinear operators of MFEM imposes the new displacement at the end of the beam, the first Newton iteration is such that all the deformation is located inside the first element. So the problems first becomes more and more important as the mesh is refined and it finite strains. We have currently severe divergence of the Newton algorithm due to the geometric stiffness matrix. And to solve this issue, in most mechanical solvers that I know, we usually do a prediction of the solution based on some tangent problem to in such a way that the first estimate of the increment of the strain is, I would say, not concentrated on the boundary elements, but over the whole structure. So we have opened a discussion also on this issue, but we were not able to implement this prediction so far. So in the example, we have done a lot of testing and benchmark on nonlinear problems. So this is typically the geometry of a nudge beam, which is in tension, and we describe it in finite strain and in the logarithmic space. And we compare different solvers, PETC, MAMS, and Hyper with the Boomer preconditioning. And what we have seen, I won't comment this very far due to lack of time, but we have good, strong scaling in this case, even in the nonlinear parts, with something which is very nonlinear in this case. And we also made a lot of tests on periodic meshes. So you could have access to this talk afterwards. Indeed, even this is the worst case scenario for the MFEM-MGIS because we systematically do nonlinear computation. So if we compare computational times with pure MFEM for a linear problem, we see that the overheads due to our library in this worst case scenario, which is purely elastic, are, let's say, moderate to low. So it's quite satisfying in our own view. So we also do many tests to check the strong scaling of solutions. So it works pretty nicely. So in conclusion, what was done, we have an API which is very high level and declarative, which is suitable for engineering studies and the upcoming integration in our platform. We have added multi-material support in the sense that part of the mesh can have a totally different behavior in the mechanical sense than the other part of the mesh. And we have the ability to handle arbitrarily complex, small and finite strain behaviors, knowing that the behaviors are set at runtime via dynamically loaded libraries, which is generated by MFront. What will come next? We have to make our code more robust and typically deal with this issue of the boundary condition, and this is critical. We have to write some more documentation and example, and this is urgent. We have started developing extension to other physical phenomena such as nonlinear transfer, diffusion, and non-local mechanics, and it's pretty much easy using the code generation tool that we have developed for concept of behavior integrators. We haven't started working with adaptive mesh refinements, mostly because it requires new data structures on an image size to handle the internal state variables at the integration points. So it's some kind of prospective future work. We have to add additional boundary condition, and we would be interested in any work done with MFEM in contact and friction. We also plan to port the library to GPUs, but this requires a tremendous amount of work on the MFront and MGIS side, and we will work on this issue next year. And last but not least, support for partial assembly, etc. So thank you for your time and attention. I hope I wasn't too long and gave you some pointers to other resources about the project and MFront in general. So thank you for your attention. If you have any question, do not hesitate.